Hello everyone, and welcome to this Wintellect webinar where today we're going to be talking about Azure networking for developers, and we're principally going to be focused on some networking concepts, some of the basics of networking in this video, and then we're going to talk, this webinar, and we're going to be talking a lot about infrastructure as code as well. So kind of the nexus of those and how that relates to Azure. So I'm going to make remarks as we go through this about where these concepts apply and then how these relate to the infrastructure as code piece, which we'll get to at the kind of with some demos towards the end. So with a little bit about who I am, I'm Blaze Stewart. I'm the architect at Wintellect. I am been with Wintellect for about 5 years now, in various different roles, and I work a lot in the Azure space of dealing with Azure infrastructure, platform as a service, development, and so I've kind of walked the both sides of the wall, so to speak, in infrastructure and dealing with networking and all that. And then also been a developer for part of my career as well. And I've done both on Azure as well. And so I'm going to try and bridge that gap in 1 hour, which I know is probably impossible, but I'm going to try to do some justice to this. And depending on how this goes and their questions, hopefully we'll have maybe some follow-up webinars in the future to kind of address some concerns, and we can look at other things and technologies on Azure as well. So without further ado, let's go ahead and get into the content, and we can have a look at that. So first things first, let's talk about who Wintellect is. Principally, Wintellect is a development and training company. We focus principally on the Microsoft space, so that would be anything in the .NET stack, Xamarin, Azure, app services and that kind of thing where you can run apps, and Azure itself. So we do a lot of work with Azure consulting, like moving workloads to Azure, how to create new workloads on Azure, how to create VMs, infrastructure on Azure, all that kind of stuff. And we also do training in those same kinds of stacks as well. So we have on-site training where we bring an instructor to you. Well, in this new world order where we have everything kind of in a virtual sense, we can do this online as well. So if you want to get our instructors to train your developers, we can do that virtually as well as on premise. Here in this quarantine state, we're doing it all virtually now. So you can definitely get training even though we're not in a building somewhere doing that training. And we also have an on-demand training site that we do. It's called Wintellect Now, and that will that's something that you can go out to sign up for and get training from Wintellect folks, and those are tailored for developers. It's got Azure related content as well as other topics on that as well. So if you're sitting around doing nothing while you're in quarantine, it might be a good thing to go check that out and skill up on a few new things on Wintellect Now. So about Wintellect, I now want to dive right in and just start talking about networking on Azure. But I'm going to start with IP addresses, because fundamentally this is where networking comes in, and this is where it all starts with whatever it is that we're going to be talking about. So a lot of what we're going to be talking about today is some of those fundamental networking 101 type concepts that in my experience, developers kind of have an idea about, but they're not overtly familiar with. And I'm not going to be able to teach you everything there is to know about everything in networking, but I hope to give you some idea about what it is, enough to where you can understand how networking works and then how this relates to Azure. And that's kind of what the first part of this webinar is going to be talking about. And it really starts with the IP address and what this means for us. So if we were to look at an IP address, there's kind of two parts to every IP address. You have what they call the network portion, which is this first part here, and then the actual host address. And if you were to expand this 192.168.0.3 out into binary, you would end up with an address that looked like this in binary. And you've probably seen constructs like something called a subnet mask or a CIDR block before. And really all of these things are doing is determining which part of an IP address is the network address and which part of the IP address is for the host identifier. So in the case of this particular IP address, if I have a 255.255.255.0 subnet mask, I'm basically telling this that I have up to the first octet is full for the networking address, and the second octet is full, and the third octet is full. So that means I have a 24-bit octet network address, and then I have a 8-bit network identifier right there. So that would be what is highlighted in blue here. If I was to do that in what they call CIDR notation, that's where you typically have the first practical address in the block, and then you have a slash, and then this expresses the number of bits of a particular IP address that are for the network. So in this case, it's expressing the first 24 bits of the address are for the network address. So again, these first 3 octets are for that. And this is really, this subnet mask and this /24 communicate basically the same thing. However, this right here, the CIDR block notation, is typically what you'll find in a lot of documentation because it's a little bit easier to write. There's some technical differences between those. I'm not going to get into that, but for practical purposes, if you see a subnet mask, it's really just representing the number of bits dedicated to the address, and the same thing with a CIDR block as well. So you will see these used in network configurations depending on which ones you're using, but for most pieces, that's what you want to notice. And for most of our purposes today, we're going to be looking at this CIDR block notation where we can talk about IP ranges based on this notation here, and we'll look at when we get to some of the things later on in this. We'll talk about that. So whenever you have an IP address, we also have to deal with IP packets as well. And so IP addresses are a part of the IP experience or the networking experience. So every IP packet that gets sent on a network, it has two IP addresses associated with it, and then 2 ports associated with it. Now, the IP address is both a source IP address and a destination IP address, and a source port and an IP and a destination port. So typically on a packet, it's going to use the upper range of the available ports. That's typically a 16-bit number. So you have up to like 65,000 ports available for a given IP address. It's in the upper range of what is available to the ports available for a given IP address. So typically anything above 63,000 is reserved kind of for the source ports on an IP address, and the bottom is for destination ports that are opening and listening for incoming traffic. And then the destination is the destination address of a given packet. So every packet that your computer sends has these 4 basic pieces of information on it, so that when it starts traversing a network, it can know how everything in between that, the source, that is your host, and the destination, that's the server you're trying to contact, will know how to route that packet. And so basically what we have something like a picture, say just this cat image here, and an IP packet there's no way to take this whole image and send it in its entirety across the internet in a single packet. So what a packet will do is typically divide it up into pieces. And I can take, say, like maybe this single packet here, and then I can take something and wrap it in an envelope that has the data. This is the datagram portion down here. That's that piece of that entire image. And then I have wrapped around it a source address and destination, a source address and port, and then a destination address and port associated with it as well. And then for all of those various packets associated with this image, they would simply just be sent over the wire and then they would be reassembled on the receiving end based on some other information associated with it with the TCP protocol that would reassemble those on the other end to give you this image of this cat, although it was chunked when it was sent over the wire. So the IP packet uses the IP addresses as part of the packet, and then the payload that's a part of that as well, which is this envelope as well as the datagram that's a part of that. And so whenever you have an IP packet sent across the wire, you have all that information as a part of it. So how does that get routed between point A and point B? That's where routing comes in. So routing is really the magic of how networking works. Now, the way routing works is based on on the destination address of that route. Then what happens is you have something called a route table. And the way this works is based on the networking address, the destination address of that packet. Like what we just saw on the previous screen, you will see a destination of 192.168.0.3 or whatever it might be. what the route table, every machine has a route table. Your computer has a route table, your phone has a route table, the router on your internet has a route on your broadband connection has a route table. It's how that this table is basically a lookup for that tells a router, your computer, or anything like that how to send a packet. And every device that's connected to a network has one of these in its memory, currently running right now, that will tell any packet that is received on that host or is being sent by that host what to do with it. And typically with a packet that's being sent, it starts with the destination. And what it attempts to do is match that packet against a destination and a net mask. So this net mask we saw when we looked at an IP address determines how many IP addresses are based on this first practical block within a given range of IP addresses. So what it attempts to do is it starts from the top and goes to the bottom and attempts to find a match inside of this IP address here, these IP addresses. And what it attempts to do is find a match. And when it finds the match, if there is a match, it attempts to send that packet to a given gateway or router on that network. So that's the next hop in the chain. So a packet that typically you'll have this kind of catch-all rule that's defined as 0000 and a net mask of 0000. That's kind of a catch-all rule. Typically, all routers have a catch-all rule, and it's the default gateway. So whenever you go into your internet connection settings, you're going to find a typically something that's called a default gateway as part of the IP configuration on your network, and that's because their catch-all rule in a route table is going to route anything that it doesn't match to that default gateway. So that just defines the catch-all rule. But for anything else, it's going to go down the list and look for a match that the IP or the destination IP would fall into. And then when it finds a match, it's going to send it to that network's gateway or router to send it onto its next hop. So this is what allows a machine to have multiple connections to multiple networks. So in some cases, you might have 2 or 3 different IP addresses, even on the same NIC card, and each one of those different IP addresses can send traffic to a different route, to a different router, because the same physical network can actually have multiple subnets defined on it that each have their own different routers. And the route table is what is on the host machine that's going to know where to send that particular packet to. So whenever I have a match, then it was going to send it to that particular router that's defined in this table. Now, if the router is defined typically as 000 like we have here, that means it's a local route. And what the host is going to attempt to do is send it to that destination directly. So that's basically means that my IP address is on the same subnet as the destination IP address. And so rather than try to send it through a router, it's just going to attempt to send that packet directly to that host without going through a router. But in the case where it might see something like this right here, 15.16.0.0, but my destination is not local and it's not in the catch-all rule, then it's going to attempt to route it to that one's particular router or this one's particular router, and so on. So depending on how you have those rules configured depends on what the route is going to look like within the context of that given table. So this is a basic example of a route table. Some of these for your local host might have 10, 15, 20 records in it. Some for the routers on the public internet will have literally millions of records in them because it's handling traffic from all over the internet. So all of this is to say that there's a lot of different ways to handle traffic. What are the metric over here is priority. Now this over here will typically, if you have a 2 routes that meet 2 destinations that have that can be found in the same rule and 2 different rules, it will look to the metric to determine the priority of that. So if you have the metric, typically the higher metrics get a priority over those as well. So you go down the metric list. If you find a higher metric, is going to prioritize that route, and then ultimately you end up with a catch-all right here that will end up picking up those routes and sending it on to the next route in the table. And some questions associated with this. What does it mean to have two destinations? You don't have two destinations. These are some questions that have been raised. And what is the route table associated with the NIC? A route table is not associated with the NIC. And are there some route tables that work for IPv6? IPv6 works the same way. It's just the IPs are bigger. So you have instead of a 32-bit address, you have I think it's a 64-bit address. I can't remember how long it is, but there's more data available, so you end up having longer ones in there. So is a metric prioritization rule when the port allow port? Route tables have nothing to do with ports, and we're going to talk about ports later on. So route tables is strictly for IP routing. So let's talk about how routing works. And talk about, maybe this will help clear up some of the concepts we're talking about. So let's suppose we have a local area network, and I'm running 2 laptops and a phone on this, and I have a router here that's my default gateway for all of my devices. And over here I have a couple other networks. I have this one over here, and notice that these have the same edge address right here. Now, these 192.168 those are private IP addresses that are associated with each of these local area networks on both sides of the wire. Now, how this enables me to send packets between two networks that have the same IP ranges is through something we call destination natting. So remember that destination IP address that we have, and source natting. And natting is how we can have multiple devices on a given local area network go through a router that might have only one public IP address, so the public internet. So this one has a public IP address of 11.12.13.14, and this one has 15.16.17.18, and then I have a router on the public internet that has 23.24.25.26. And so these are out on the public internet. So let's say that my phone raises a request and it has a source IP address of 192.168.0.2 and a destination of 192.168.0.3. Well, what's going to happen is it's going to end up going through my router. It's not even going to get routed really. It's just connecting to the switch that's baked into this router and getting sent directly to this host over here, which is 192.168.0.3. Because its destination is this IP address here, and the source was from this phone. There's nothing that needs to happen to that packet, simply because it has, within the context of that packet, all of the information needed to route it from one host to the other one, because both of those hosts are on the same network. So the route table would tell this packet, hey, just send it directly to this host. No need to route it. None of that needs to happen. It simply can go right through the switch to that host. And that's what that device is doing, that router/switch right here, which is typically what you're going to find on a local area network, like a home network or a small office, home office. In an enterprise network, typically switches are different devices from a router. But in a small network, those are typically all combined into a single device, and you have a switch, router, access point. An access point is just a wireless switch, and you might have a wired switch as well. So those are all rolled into one device. But on an enterprise network, a switch is typically a separate device from your actual router. But for simplicity here, I'm combining them into one device. So the next packet that this one wants to send to is to the other host on my network, and it's simply just going to go right to that host as well. Now this next one, I have the source as 192.168.0.2, but notice the destination here has changed, 15.16.17.18. Now when I send that, it's the router is going to see now, like this one's going to route this packet to its default route because it can't route this locally. So it's not going to attempt to send it. So what ends up happening is this packet gets sent to the default route, which would be 192.168.0.1 for my network. Now what the router is going to do is, because it can't send a private IP address that is something in the 192.168 range over the public internet, it's going to do something called source natting. So what it's going to do is substitute its public IP address for the local address here. So notice what it did here is it changed the source IP address from the local address to its own address, and then that packet can then be routed over the public internet. And then it's maintaining that, and then it goes to its next hop, which would be some router on the public internet. There might be multiple steps. For simplicity, I only have one route here. And then the internet doesn't, the public routers on the internet don't change that source or that destination route simply because it doesn't need to. It's just routing it across the internet to some destination router, which is defined by this IP address right here. Now, once it reaches that IP address, the actual destination for this is not the router itself. It's actually intended for some port. So what this is going to do is it's going to do something called destination NATing, which network address translation is what NATing stands for. And what it's going to do is it's going to transform the destination IP address to the internal address for the web server that this packet is bound for. And then it's going to then forward that packet onto that backend server. So on what happened back here on my original one is it did source NATing, and over here it's doing destination NATing. Now, one of the things that you can do with the with NATing as well in this case is you can also do port mapping. Sometimes you might have a backend server that's using a different port number, like port 8080 is a common one for backend servers, but you might be able to do port mapping between port 80 to port 8080 on the host. But for most practical purposes, destination NATing and source NATing, or DNAT and source NAT, are both happening on most of the packets that you send out of your network. So me speaking into the microphone right here, all the voice traffic that I'm sending over this is getting encoded as IP traffic on my local network. It's hitting my router on my local network. It's getting source NATed from my local network here onto my ISP on my public address. Then it's going up to the servers on GoToWebinar, and then it's turning around and broadcasting that down to your local network. And then it's probably getting destination NATed based on the fact that you're running a locally connected client, and it's getting destination NATed back to your client. So all of this is going on in real time in lightning fast speed, and we don't even realize it most of the time. And this is happening millions of times per second on your network. And so that's basically how this works. So any questions related to this? But dynamic change can change that IP. Dynamic IP addresses can change at any time. And in any case, that dynamic IP address can change. Typically what happens with dynamic IP addresses is it will end up using the new IP address for that that destination NATing or that source NATing, depending on what happens. Now, typically network hosts on the internet that are running on, say, Azure or some on-premise, those are going to have some kind of public IP address that doesn't change often, and that's so that you can have a DNS record that is the Wintellect.com associated with some IP address. Your host on your network, because you're not hosting services, can change. And that's called a dynamic IP address. That can change, and it has very little consequences for hosting services unless you're actually hosting a web server or something like that on your network. And then you can use dynamic DNS to kind of solve that problem. So that's what you're seeing here. So that's kind of an overview of how networking works and how routing works on the internet, and using route tables and how destination and source NATing works on the particularly on networks. Now, all this applies to Azure, because on VNets, what we'll see with Azure VNets is you will see public IP addresses associated with backend IP addresses. So all your servers on Azure typically are going to have a private IP address associated with them. And if you were to go into the network configuration on that and look at it, you're not going to have a public IP address on that backend server. Now, what Azure is going to do is it's typically going to do a one-to-one NAT between a public IP address and a backend IP address if you were to associate a public IP address with your server. Now, you can also do load balancers in front of your servers and associate public IP addresses with the load balancer and just have it load balance among a bunch of different backend private IP addresses as well. And we're going to look at some of those schemes in at a few slides here. So that's how this relates to Azure. And Azure also lets you have what they call user-defined routes. So within the context of Azure, you can configure essentially the local router for your VNets to have custom routes that are defined. If you want to have something like a network gateway, rather than just use the default network gateway that comes with every VNet that you stand up on Azure, you can put something like a Palo Alto or an Azure firewall in front of all of the servers on your network, on your VNet on Azure, and then define all the traffic to route through that server, either as the catch-all rule for your route table, or even for local traffic as well, if you want to do filtering of traffic that way as well. So the ability to define user-defined routes based on source and destination, or some things that you can do within the context of route tables on Azure VNets, and you can also define some things related to those if you want to stand up virtual network appliances on the Azure as well. So we talked a little bit about how routing works. I'm going to shift gears and talk about packet filtering, which is another topic that relates to packet filtering Azure on what we might call network security groups as well. So packet filtering is where ports come into play. So with a packet filter, what we're going to have is a packet filtering is the ability to filter packets that are coming into your network. So this is basically your firewall rules. And going back to what we said about IP addresses are one way to create packet filters. And you can also create packet filters based on ports as well. So remember we talked about IP packets. They all have source IPs, destination IPs, source port, and destination port. So we can use packet filtering with network security groups on Azure to define rules that will filter out traffic from any one of those basic pieces of information that come through on every packet that comes into your network. And network security groups give you the ability to define these rules that you can apply either at a virtual machine level or at a subnet level on Azure. And we will look at some examples of this when we look at ARM rules, ARM templates. So every packet filter on Azure or any device really starts with a priority, has a priority associated with it. And it's similar to a route table where it does a first match. And so it basically starts at the first rule, and if it matches, it looks to match a rule, and then it looks at the action or the policy to take place. So basically, what the packet comes through, I'm going to say this is the name of the packet, block North Korea. This is the CIDR block. I don't know that this is the actual CIDR block for North Korea, but if I wanted to block all traffic out of North Korea coming into my network, I could basically put in a CIDR block rule that is use that slash notation to say that anything out of North Korea I want to block, and that's the number one rule on my priority filter here, on my packet filter here. And so if I say anything that has a source IP address of this that falls within this range, I'm going to apply a block on it. It doesn't matter if it's bound for port 443 or port 80. It's going to block it. Because it's the first match it finds, therefore it's going to block it. Doesn't matter if these rules are allowed, it's going to block all that traffic. Now, however, if I had some rules coming down the pipe, say I have something from, say, England, it doesn't get blocked here, and it's routing it to port 443, okay, I'm going to allow that. And so that would match against this rule here, and that would be allowed. Or if it's port 80, the same thing happened here. Now, if none of these rules are matched, it's going to hit a catch-all rule, and it's going to say any source IP, any destination IP, any port number, block it. And so that's a catch-all rule that's basically saying if no rules match it, block it. And so you will have, generally speaking, this is a default rule on every packet filter you create, because otherwise you're just going to be allowing everything. In fact, Azure won't let you delete the default block rule because it's basically the reason you have a packet filter in the first place, is you want to be as pessimistic as possible and only allow for what you want coming into the network and block everything else. And so you open up ports rather than just allow all. It doesn't make sense to have a packet filter if you're not blocking things at all. And so this one you have the catch-all rule that will allow you to block anything as well. How to the block. What is block NK? I'm looking at some of the questions here. What is block NK? That's just the name of the rule. That's what I call it, block North Korea. And the prioritization works by, it evaluates this one first, second, third, fourth, smaller being higher priority, and it goes down the list. So that's basically what that how that works. And that's how a packet filter works. So to animate this, I have the same packet filter here. Basically the rules here. I have a packet that has a source IP address of 20.21.22.23 and a destination of 15.16.14, 17.18 and a port of 80. So that one's going to come in and it's going to get routed to the back end to this IP address here. And I can do a destination port here inside of my packet filter if I need to. And some packet filters allow me to do this, some don't. Network security groups don't do this. It's going to do it by default depending on the private IP associated with a public IP address. And so if you have a private IP address associated with a public IP address, you don't have to define this rule right here. It's going to do that automatically for you. But in the event that I don't have that, I'm just using something like a Palo Alto or something like that, I have to define these rules more explicitly. Now, however, if I did have the destination port assigned to port 80, my policy is to allow that. That's why that packet got through. It's because the match here was on port 80 and I am defining the rule based on port 80. So my next example is I have a source port of 21.22.23 and a destination of 15.16.17.18. So this one's going to come through and it's going to hit the firewall and it's going to get dropped because it wasn't none of these rules matched it. But what it ended up happening is it got caught by the catch-all here, and because none of the rules match it, it dropped the packet. So my next example here is a source IP address of 175.45.176.33, destination, same destination, and port 80. Well, what's going to happen with this one is it's going to hit the firewall and get dropped too, because even though that it would match this rule here, it ends up getting blocked by this rule here because it has a higher priority because the source address fell within this CIDR block here. And so this higher prioritization here blocked that rule and it never got down to this HTTP rule because this one has a higher priority in my packet filter here. And that's how network security groups work, is basically you have a priority rule, and then if you have a higher prioritization in that rule, then it's going to end up blocking that. My personal firewall I have here at my home, I have geo-blocked a number of countries that I don't want to. I just block all countries from these sources because I just do that because a lot of hackers are from 75% of the world's traffic from hacking originates from 9 different countries. So if I block those 9 countries, then I'm going to be blocking 75% of malicious attempts on a network just out of the gate. But if I simply block those countries from a source IP range and from a destination IP range for that matter, so I can do it from both ways. And if I need to open it up for special cases, I can, but I typically don't do that. I just block it wholesale. And so, and then I'm also pessimistic from ports as well. I only allow certain ports out and allow no ports in. So my network is, I have a very tight network on my LAN simply because I'm paranoid about security. Because I've worked in security before, and I simply just know how where all the hacks come from and all that. As I'm just a little bit paranoid, maybe call me that, but whatever. So what are the 4 things that every network must have? And these are all provided by Azure VNets. We looked at routers already. Through route tables. Every network is going to have a switch. You don't have to worry about that on Azure. You have a DHCP server and you have a DNS server. A DNS server is the thing that turns those names like Wintellect.com into an IP address, so you don't have to memorize a bunch of IP addresses. And a DHCP server is what assigns network addresses on a network. So I have a DHCP server on my network here on my home office, and I have it explicitly defined. Now, most routers that you get from the store have a built-in DNS server and a built-in DHCP server, as well as a built-in switch and a built-in router, and all that functionality is combined into a single device. Most enterprise networks are going to have multiple DNS servers as a part of them. So it has a primary and a secondary DNS server as dedicated devices. Same with DNAT, DHCP server. It's a separate device from an all-in-one device. The switches are different and the routers are different. So on an enterprise, these are all broken out into individual devices or servers. On a home or small office networks, it's all combined into a single device. That's typically your router, your internet router that you have, that you get from your ISP, or the one that you bought at Best Buy or something like that. But regardless, all of them kind of have all these basic functionality built in. And so yes, you can have more than one DNS server on a network. And a country was, what are the 9 countries? How can you find this list? I Googled it, and I don't remember what they are. I just Googled it. I found them. I set the rule up and forgot the countries. What is the difference between a switch and a router? A switch is a low-level device. It's what actually does the actual the network, the Ethernet switching. That is the Ethernet switching that is defined by the protocols that are used by Ethernet. So a switch can handle any network protocol: TCP, IP, TCP, UDP. It can handle IPX. It can handle all those network level protocols, but it's actually doing it all at the Ethernet level. The same thing with a switch. Your wireless device in your home is a type of switch. It's a wireless switch. It's using Wi-Fi, the Wi-Fi standards, but you can run any protocol on that Wi-Fi standard, be it TCP or UDP. It can be use IPX. It can use ARP, which is used for address resolution protocol. It can use the DHCP protocol, which are both not IP-based protocols. They're used for discovering services on a network. They're not IP-based protocols at all, and all of that runs at the Ethernet level. That's what a switch does. A router, on the other hand, is something at the IP level, which we're going to look at a slide here in a minute that will speak into this a little bit. It's called the OSI model. In fact, I'm going to switch to that here in a minute. I think this is relevant to that conversation. A switch works at this level here, the data link layer, and a router works at this layer here. And so this would be your router right here for the this layer, and then the data link layer works for the switch here as well. And then most developers are going to be familiar with this layer up here, that's the HTTP, the protocol layer, when they're actually dealing with that kind of data. And so on Azure, you don't these kind of 4 things that we were talking about here. You don't have to worry about the switch, because that's more of a physical thing, and you have some control over the router with the ability to define route tables and user-defined routes. You have some control over the DHCP server if you want to have if you want to assign addresses to virtual machines and other resources on Azure. You can definitely do that. You can also tell the DHCP server which DNS server to use. So if you want to use a custom DNS server on Azure, you can, or you can use the built-in DNS server as well. And so you have some control over routing and complete control over this and complete control over the DNS, but you don't really have to worry about the switch on Azure, because that's all below what you have available to you on Azure. Azure basically gives you everything from the route level all the way up through to the application layer, which we'll look at. That's what that OSI model is. But for most intents and purposes, really what you need to focus on is understanding the TCP protocol, how it works, how the routes works, and how packet filtering works, and how those destination and source filtering works, as well as the routing on those source and destination for each given packet as well. And so that you can have you can have routes associated with those user-defined routes on the route tables on Azure, as well as setting up rules inside of network security groups for packet filtering purposes. The question is, assuming that you're meaning the managed switches are not just dumb switches. Managed switch, yeah, kind of. Managed switches, that's another question that came through. Managed switches are a little bit more context aware. Managed switches are typically going to have things like VLANs associated with them. A dumb switch is just something that just does Ethernet switching. It doesn't really care a whole lot about the packets, but managed switches give you the ability to have some way of shaping network traffic, doing some prioritization of that traffic, setting up some things like VLANs and SOGLAN. But managed switches don't get involved in routing packets. That's not the job of managed switches. Managed switches don't really deal at that layer. They deal with at the low layer, the low level traffic. And on Azure, you never really have to deal with managed switches at all because you don't have no control over that. There's no concept of VLANs on Azure. There's there's no VLAN tagging on Azure. There's none of that QoS on Azure. There's none of that kind of stuff that is involved with managing switches because you never really have to touch the switches. Microsoft manages those for you. You really have to worry everything from the route layer all the way up through to the application layer. So with that in mind, here's some common schemes that you might have on Azure where you have a VNet that's defined. And this is where we have those IP ranges defined. So whenever I create an Azure VNet, I have to define what's the CIDR block range. That's that /24 notation that I want to have on my entire VNet. Now you can have multiple IP ranges associated with an Azure VNet. And so this is going to be /16, which basically means that the first 2 octets of this are associated with the IP space that's associated with this VNet. And then I can carve that VNet space up into what we call subnets, which are some subset of the IP space associated with this VNet. So in this case, I have a /24 VNet, and that's going to be basically the first 3 octets associated with the network address for the subnet, and everything else after that 4th octet is basically going to give me the host address on a given network. So the host associated with this subnet will have anything like 10.0.0.5, 10.0.0.06, and 10.7. And typically the addresses on Azure are going to start with the 4th available IP address in that range because it reserves the first IP addresses in any given range on Azure for Azure related services, and then it gives the user the ability to find anything beyond that. So typically you're going to have IP addresses that are going to be assigned sequentially, starting with typically the 4th address going all the way 5, 6, 7, and so on. And if I was to have a virtual machine on Azure, what I can do with that virtual machine is I can have a NIC card associated with one subnet. I'm going to have a secondary NIC card associated with another network, and it would have 2 addresses on that, and it can span both subnets. And then what I can do is I can set up these network security groups inside of either at the subnet level right here or at the virtual machine level to only accept traffic from, say, this subnet. So if it was coming in from the cloud, if I was coming in from the cloud right here, I can only accept, I'm going to block traffic that I'm going to allow traffic from the internet on this network security group, but I'm going to block traffic from the internet on this network security group. So this will allow me to have some layers, some network segmentation here right there. And so this one will accept, they say this is my web server, it's going to accept traffic coming in off the cloud, and my network security group accepts that. But this network security group will not allow traffic from the internet right here. Instead, the packet filter is going to block inbound internet traffic, but it will allow it from, say, this subnet here as one of its rules. And so then I can have this machine talking to, say, maybe a database VM in the back end, and my application is running on this front end subnet, for instance. So that's how I can define. That's how I can define networks using virtual machines on an Azure VNets, where I can have some segmentation as well. Some questions coming in is, can we increase the IPs of an existing subnet on Azure? Yes, you can. That's very easy to do. Can we make a DHCP server a static IP address? You can't. On Azure, on a VNet, you can associate a static IP address with a given virtual machine. You can reserve that. And a DHCP server, in most cases, will, depending on the DHCP server, it does allow you to have network reservations on the DHCP server. So if I want to assign a specific machine a specific IP address, I can say, every time this machine comes up, assign this IP address, and it will prevent other machines on that network from utilizing getting assigned that same IP address. That would not prevent a machine on that network from hard coding that IP address. Now, Azure won't let you hard code an IP address in the virtual machine settings. It would actually sabotage the machine and you wouldn't connect to it. However, it will within Azure on an Azure VNet configuration, you can assign an IP address to a VM, and then that becomes essentially a static IP associated with that virtual machine, although it's being brokered by way of the built-in DHCP server on an Azure VNet. So you can assign those IP addresses, and what that allows you to do is have something like virtual appliances on your Azure subnets that act as firewalls. So you can have a Palo Alto running in a VM or something like that allows you to have something that's beyond what is provided by network security groups, or having other type appliances like F5s, for instance, that F5 devices that will allow you to do some kind of ingress controls or egress controls in and out of Azure through an appliance type experience as well. So those are some ways to shape the traffic here using network security groups and routes. And there's a lot of different ways to manage this. Network security groups, though, allow you to have some internal segmentation inside of your Azure VNets. Another question came through is, can you configure DNS servers for all the servers in multiple VNets? There is a way to do that, and it's kind of outside the scope of this call, but of this webinar. But you can do that through what we call VNet peering, and with VNet peering, you can have multiple VNets, and then you can peer those together and then define routes within each of those VNets to route traffic out to what we call a hub VNet. And every peered VNet that's connected to that is a spoke VNet. And you can use those user-defined routes within the VNet to contact that DNS server that is in your hub. And so they can all share a common DNS server. And that way it allows you to do that. What's the difference between global VNet peering? What's the difference between peering and global VNet peering? Global VNet peering and VNet peering are more or less the same. It's just the costs associated mostly, and on Azure. So let's look at we've already looked at the OSI model a little bit in brief. I want to talk about this briefly here, mostly from the perspective of what we're going to be looking at when we talk about network security groups, and what we're talking about router load balancers and application gateways. So on an NSG, it works principally at this layer here, layer 3 and layer 4. It's typically called a layer 4 packet filter, and with TCP and UDP as well as IP, the ports are associated with layer 4. The actual IP addresses are for layer 3. And then up in the higher in the stack, what you see is the application layer. Now on Azure, you have an application, something called an application gateway, and that is a load balancer that works with HTTP. So on Azure, you have basically the ability to control these top 5 or so layers through various means on Azure, through route tables, through network security groups, and so on. You can do, and so if you were to take some of those schemes that we were looking at a minute ago, say those load balancing schemes, and we were looking at those, and we had on Azure, we might have an Azure load balancer that's standing in front of a set of virtual machines, and that is connected to an external IP address, and that looks like this. This is a layer 4 load balancer. So this is basically doing TCP load balancing. Incoming traffic on an external IP to a single IP address on a private network. It's one-to-one NAT here that we saw when we looked at NATing, and then that traffic gets load balanced between these internal IP addresses that are behind the scenes. So this would work for things like FTP or something that I don't have a load balancer. It would work for HTTP as well. It's not protocol specific in terms of the application protocol. Now with HTTP load balancing, we have something called an application gateway, and it looks a lot like a load balancer does. The main thing that this thing does, though, is it does it at the HTTP level, and it does load balancing among web applications. So you'll see application gateways on Azure that's principally targeted for layer 7 for the HTTP protocol. Now, a load balancer TCP load balancer is much more low level in the stack as a layer 4 load balancer, and it's principally designed around the layer 4 devices. So that would be for anything that's kind of outside the scope of an application gateway that you would want to use for a load balancer. Now, with a application gateway, you can pair those with network security groups to define not only the application gateway rules, but the network security groups can act as a packet filter as well, so that traffic is filtered before it even hits the application gateway. So if you want to block, say, North Korea, you can do that, and it would never hit the application gateway. You can also do packet filtering for TCP load balancers as well. So if you want to do packet filtering before you ever hit that load balancer that we just looked at, you can do that as well. And these also work for platform as a service as well. So with app services, you can define something called a private link, and it basically exposes a private IP address on a subnet on Azure, and it allows you to have an application gateway in front of it, or even a load balancer for that matter, between several app services as well. And that would work for a load balancer if you wanted to put multiple instances of a SQL database, for instance. I mean, I don't know why you do that, but you could. Through private link, you can expose TCP-based traffic as well, load balancing that among app services. You could do that among any myriad of different things using application gateway or app services. And through private link, that is one service that allows you to do that. Now, what is what load balancer, and some questions that just came in related to load balancing. What load balancing am I talking about? Load balancer back here on this slide. This is TCP. This is layer 4 and layer 3 load balancing here. That's what Azure Load Balancer, that's what it's called, Azure Load Balancer. That's layer 3 and layer 4 load balancing. And that's just strictly TCP load balancing. This one right here is HTTP load balancing. So this is layer 7. And so this would be done at the protocol layer. And then this one right here, this is layer 7 as well. So it's an application gateway. So this a different kind of load balancing coming in there. So layer 3 is IP based only. Yeah. So typically a load balancing scheme is only going to have as layer 3 and layer 4 could sometimes get blurry depending on how the load balancer is configured, because a load balancer can do things like port mapping as well as load balancing among a pool of IP addresses as well. So that gives you the ability to do some of both layer 3 and layer 4. So that's why it's typically called a layer 3, layer 4 device. It does both. And so it works with IP addresses as well as port numbers. So that's the key difference as well. So with that in mind, we've kind of done, we've looked at some of the differences between, we've looked at kind of some of the things available on Azure as it relates to networking concepts, network security groups, and so on through the slides. I want to flip over and look at some examples of network as infrastructure as code and how these relate to ARM templates, because this is where networking and code start to come together. And it's whenever you start to build out network infrastructure using code. So let me pull up some examples of this, and use ARM templates as a way of discussing code as it relates to infrastructure. So most guys on that rest in the development space don't really ever have to deal with the actual managing of switches and local area network traffic, or managing routers, or any of that. However, when applications get more and more automated through DevOps experiences, the need for networking knowledge becomes important, because oftentimes whenever you start talking about deploying environments to something like Azure, you're not going to be deploying new environments to existing infrastructure. You're going to be starting from scratch. And the reason why you do that is to keep costs down and to make applications more dynamic, so that you can deploy these applications from scratch, literally from no infrastructure to an application up and running with all of the networking configured, all the virtual machines configured, and the application running inside of that virtual machine. And that's what these brief demos here that I'm going to look at here. I'm going to look at this one, and if time allows, a second one. In this one, I have a ARM template, which stands for Azure Resource Manager. Azure Resource Manager is the way to do infrastructure as code on Azure. Now, there's a couple ways to do this. I'm principally going to be concerned with templates here because this is a declarative way of defining defining network resources on Azure. So with this, I have a couple of different things that I need on the resource manager that I have to have. Now, when I'm talking about ARM templates, the only thing that is absolutely necessary in an ARM template is the resources you're going to be using. You could hard code everything in a resource, but it doesn't make it reusable if it's all hard coded. So what you have associated with that is parameters and variables. Now, parameters are things that you can input into the ARM template, and that's done by way of parameterizing it. And then you can have variables that are some kind of things that are values, key value pairs that can be used inside of the resources that can be reused. And in this particular template, I have a number of different variables that I'm associated with this. Notice I have some subnets here and some IP addresses here, and I have some subnet names. Now, what this is doing is I'm using these parameters here to define the networking that I have associated with that. And I have a networking here that I have associated with my IP addresses here. So that I'm going to be defining down in here. So what I have here is I have these variables set up, and I have associated with it a public IP address, and I have the public IP address as dynamic. I could put that as static if I wanted to reserve an IP address. And then I'm building some variables down here related to the virtual machine. So next thing I come down here and do is I have to define a couple of different things. I have to define an IP address. So this becomes the public IP address that I define. So this is allocating that IP address for the public-facing IP address for this particular virtual machine. Next, I define down here the virtual network. So that VNet that I'm going to have associated with this virtual machine, I have to define because every virtual machine that I deploy to Azure needs to have a VNet to attach to. And so this one is where that address space that I talked about comes into play. So that parameter that variable that I have here, that address prefix gets assigned here. And then down here to start defining my subnets. And the subnets get defined by that subnet prefix, which is that /24 I had defined up here in my variable. So there's my address prefix, there's my subnet prefix. And so that defines my network. And so once I have my network, my IP address defined, I have my subnets defined, what I can then come down here is I can start defining my network interfaces as well. This is my network interface for my virtual machine. And it depends on the virtual network, the security group, and the actual public IP address. And I'm basically saying I want to use a dynamically assigned address that's within the private IP space of my infrastructure here. So this is going to be associated with that particular that subnet that I created up when I created my VNet above. And it's also going to be associated with that public IP address that I have associated with it above. So this is going to tie that public IP address that I have allocated above with the actual private IP address that gets assigned to this virtual machine. So it's going to do some of that NATing that we talked about earlier in the webinar. And then this associates it with that subnet. Now, in addition to this, I have down here associated with a network security group that I have defined here. In this particular instance, I'm doing some packet filtering. I'm setting this up to assign some packet filtering to this virtual machine for the application that I'm going to be running in it. So the application that I'm going to be running, actually two apps that I'm going to be running in this, need 2 ports that are exposed, 3 ports, I think. Port 22, this port right here, 36,330, and then port 443. So this is going to expose SSH. It's going to expose this one here, and then it's going to expose just some kind of random port here. And this port right here is for web services, that's for SSL. So if I could take this ARM template and deploy that, which I will in just a second, what this is going to do is it's going to spin up a virtual machine on Azure with everything already defined in it. And what it's going to do is it's going to allocate all these network resources, and then it's going to create a VM and then attach that VM to that network resource, assign an IP address, assign a public IP address, and then it's going to do some behind the scenes things by associating with it a script. That script is going to install the application and provision the virtual machine to run the applications that I'm doing. So I can have associated with it a fully automated deployment that is going to have everything I need within that context of that deployment already up and running. So let me pull over my portal here, and I can deploy this in the portal if I want to. I can take that code, and I'm going to run template here and create a new resource. And I'm going to create a new resource and copy and paste the build my own template here. And I'm going to basically copy and paste this template into this right here. And notice what it did here is it broke out the resources that I'm going to have. I'm going to have storage account. That's for to host the virtual disk. I have some variables associated with this is for the network definitions. This is for the network security group. This is for the actual virtual machine extension that's going to call a script to provision the virtual machine. And then this is finally the actual virtual machine that's going to create. These are the variables that I have defined here. And these are the parameters that I can put into this. So if I hit save, then it's going to prompt me to create a new network group here, FAA client 1, or let's call it 2, I don't know. And I'm going to call it Blaze FAH. Now what this script is actually going to do is going to install folding at home in an Azure VM. And what this will do is it will install a folding at home. If you're not familiar with that project, is basically a distributed computing project that will allow you to do protein modeling in a virtual machine so that you can find some cures for diseases like COVID-19. And so what this script does is installs it on a VM on Azure, but it also installs some Azure VM infrastructure as well. So if I fill this form out, what it's going to do is deploy all that infrastructure as well. I need to create a resource group and call it FAH client 2 and call it that. And I'm going to start this up, and it will start the provisioning of that virtual machine in the background. So it's going to start that deployment process for you. So if you want to kind of see what this looks like, I can pull this up in my GitHub. The GitHub resource right here, if you want to look at this particular example that I've got here, this is the GitHub repo for it, the 1mule/FAH client Azure VM. And this is the template we just looked at. I built this about 3 weeks ago in response to COVID-19 to use Azure resources to deploy the folding at home client on Azure to help find a cure for COVID-19. In fact, Mark Rasinovich retweeted about this particular project I did here on Azure for Azure VMs just to create the client. And I mean, it's gotten a little bit of traction, and folks have, it's been starred 5 times, forked 3 times. It's not a major project that I have going on in Azure, but it does give you an idea of if you want to deploy it on your Azure subscription, you can do that, and you will see some of the resources that it creates. So if I come back over here to my Azure subscription, I can come in here and look at the deployment. So while this deploys, I can start taking some questions now as well. So if you guys have questions related to this, go ahead and start putting those in the questions box, and we can come back and look at this and watch it deploy it as it deploys right here. So let's see. Any new questions since we looked at there? In an ARM, can I add steps to add servers in Active Directory? If so, then how? Yes. I'm sorry, I've got one question before that. With a code in an ARM template, can you do conditionals? Yes, you can do conditionals in ARM templates. ARM templates allows you to do conditionals that basically allow you to have forking in the ARM template. So in case you want to have different code branches for different scenarios, and you can do that based on variable inputs in Azure ARM templates. It's a little bit difficult to parse the code and understand it because ARM templates are so verbose. I typically will create 2 ARM templates and then have different scenarios do different ARM templates rather than try to have one ARM template to do everything. So that makes it a little bit easier to manage. Next question is, which one good is a good variable to use, or variables or parameters, or what's the difference? The difference between a variable and a parameter in an ARM template is parameters are inputs, and so whenever we looked at that form that I filled out with all the when I deployed my ARM template, those are the parameters. That's what I can put as input into the ARM template. The variables are internal values. I can't change those values externally. Those are created internally for the ARM template to use. And so I can create variables from parameters. Parameters are inputs. Variables are internally used by the ARM template to actually create resources and other things like that. So I can create variables from parameters, such as what we did in this example here. I think there's a few examples up here that I saw. If I looked at some of these parameters here, one of the things that I did down here is the VM size, some other things right here. I have, let's see if I have any examples where it's actually using a parameter inside of my variables. I don't see one in this particular ARM template. I have written where I have them. So this is using variables to do variables. The variables are used elsewhere in the resources down here, such as calling out to an external script to provision the VM, which I think is a good idea here. User IDs and passwords in ARM templates, a good idea. It's not hard-coded in there, but you can pass them into ARM templates, and that's perfectly fine for security purposes as well. Next question. If I have two NICs on a VM, can they both have the same route table? Yes, they can. Route tables are applied at the subnet level, and you can have two NICs associated with a single subnet. So yes, you can have two NICs associated with the same route table. You can have the same route table applied to multiple subnets as well, because you have the subnets associated with those as well. So that is what you can do there. If a VM has two NICs, do they both use the same route table? No, they don't have to use the same route table though. If they're on the same subnet, they'll use the same route table. But if they're on the same they're on different subnets, they'll use different route tables. If they're on the same VM, they'll use the VM route table. So you have two route tables essentially. You have the route tables that's associated with the VNet, or really the subnet in the case of Azure, and then you have the route table that's built into the virtual machine. So if the NICs are on the same VM, they use the same route table internally. If they're on the VNet, they're associated with Azure VNet, there's a different route table there, and that is associated with the subnet. So you have at every hop along the way for every packet has to deal with multiple route tables, and those are multiple filters applied to that same route. Next question is, what's the difference between a VLAN and a VNet? On Azure, a VLAN is a concept that's associated with a switch. A VLAN is where you have the same physical infrastructure on the switch. So I have a physical Ethernet switch, I have a physical router, I have all of that. And the Ethernet packets get tagged with something called a VLAN tag. And that's what a virtual LAN is called. It allows you to have let you have layer 2 level segmentation. So the TCP traffic on on that particular network gets filtered out based on VLAN. All the traffic gets filtered out based on the VLAN tags at the layer 2 level. A virtual network in the context of Azure is a TCP level network. So it's a virtual network that has associated with an IP space, and then you can carve that up into different subnets. There's no VLAN tagging associated with that, and so it's a VNet that deals with layer 3, a VLAN deals with layer 2 in the OSI model, and that's really the difference between those two. Will this webinar be recorded? Yes, this webinar will be recorded. And that's the last question as I'm seeing here. Let me review these, make sure that I don't have any. I think I answered most of these as they came through. And we looked at a lot of these questions and answers as they came through. This will be, this recording will be posted out on our website and on our YouTube channel. We will record it and post it out there. It will be available through those channels as well. We do have a couple of different things here to wrap up here. So we have you can reach out to me on email if you like. Check us out online on Wintellect.com. We will post this on our YouTube channel here at wintellect.com. And, I started a podcast. That URL is wrong. It should be blaze.net, not blazese.net. The podcast addresses though, but we are posting I just recently launched a podcast that'll be related to all things Azure and so on. We post a lot of stuff on our YouTube channel as it relates to Azure, and we have a lot of articles, and all the videos that we post on YouTube end up on our website as well. And we post a lot of stuff related to Azure resources on our various Twitter accounts as well. And if you have any questions, please feel free to reach out to me in the future. So this is so I think that's the end of it. Let's go ahead and check on our resource. It's still deploying, but you'll just have to trust me on this. I'm going to call this a wrap on the this particular webinar. I think there's some good questions, and we probably have some follow-up webinars related to networking on Azure, because I think some of the questions that have been posed here will precipitate some more advanced features on how to build some of the more advanced features of networking on Azure. So maybe something like how to build hub and spoke topologies, how to create routes, how to do a lot of some of those more advanced topics on Azure networking. It won't be tailored for developers. Like, this was more intended for developers to get a basic understanding of networking concepts and how that relates to Azure VNets, routing, and so on. But maybe in the future we'll have some more stuff that's related to IT pros, and maybe if you're a developer, you can come as well and listen to those as well. So thanks for coming out to this edition of our Wintellect webinars, and I hope to see you on future Wintellect webinars in the future. And that I'm going to be signing off now, and hopefully we'll have this uploaded very soon. Thanks, and have a good day.